Hi, I'm David Spergel, and want to welcome you to this lecture. I want to apologize because I managed to give two totally different titles for this lecture. I had gotten email, I think from Marshall Lux, and I said, I'll give a talk on the shape of the universe. And then I got an email from, I think someone from the university, and I said, well, you know, I've got this new job as foundation president. I'll talk on the role of scientific philanthropy, which are two totally different topics. And I don't see how to combine them. And the sentiment last night at the tent was to do shape of the universe, so that's what we'll go with. If people are interested in scientific philanthropy, I'd actually be very eager afterwards, if anyone's interested, to stay and just talk about it, because in my new role, I find it very valuable just to get different perspectives, tell you where I'm coming from, and so on. So I'll do that after. And I also know from many of my classmates, Larry Arata is speaking, and there's a bit, in about half an hour, and there's a conflict. So some of you may want to walk out and leave. I will be really offended that you choose Larry's talk over mine, and in some of your cases probably won't talk to you to the 45th. But,
is that a promise?
yeah, but you know, you can't always deliver on those promises. So what I want to talk to you about today is what we've learned about the shape of the universe. And in giving this talk, I also want to give you a sense of the, I would say, miraculous link between mathematics and physics. The fact that math provides a simple language in some ways that describes the properties of the universe. To give what, you know, look across science in my new hat, I am always continue to be struck by what Eugene Wigner calls the unreasonable effectiveness of mathematics. Eugene Wigner was at Princeton when many of us were here, and I had, you know, and was one of the great minds of 20th century physics, and helped shape a lot of our understanding of things like nuclear physics. So I want to begin by talking about how we observe the leftover heat from the Big Bang, the microwave background. And to do that, I'm going to first teach you special relativity, then general relativity, and that will only take about 5 minutes. So then we'll move on to talk about geometry and topology and what we've learned over the years. So first, let's begin with special relativity. The key idea to think about here is when we look out in space, we look back in time. We see the sun not as it is at this exact moment, but as it was 8 minutes ago. It takes light 8 minutes to get from the sun for us. If, you know, Mars, depends where it is in its orbit, you know, could be as far away as 30 minutes, and the further out you go in space, the further back you go in time. So when we talk about a star being 10 light years away, that means we see the star as it was 10 years ago. If you look out at a star that's 40 light years away, you're looking at a star that if you were orbiting that star, looking back at Earth, you would observe the members of class of '82 at graduation, right? And the further out we go, as we look, the further back we look in time. And, you know, we've seen these remarkable images of distant galaxies from the Hubble telescope. Those are typically sort of 12 billion years ago. And many of us in astronomy are very excited about the James Webb Space Telescope because it looks out in the infrared, and we look out in the infrared, we can look further back, and we're hoping to see the universe when it was 13 billion years ago. But today's story, we're going to go further. but we go further back in time, look at observations of the microwave background, and look at the universe as it was 13.8 billion years ago. So that's the key thing in special relativity. We see the past. Astronomy is more historical science than experimental science. We observe the universe and infer what's going on. Let's move on to general relativity. General relativity, as my academic great-grandfather, Johnny Wheeler, taught, consists of two ideas. Matter tells space how to curve, and the curvature of space tells matter and light how to move. And this was first observed now over 100 years ago, when during the solar eclipse, astronomers saw that stars were displaced because the light from the star got deflected as it moved around the sun. So a star that was supposed to be at position A was at position B. And there we go. Here's the New York Times. Light all askew in the heavens. I love this. Men of science, mostly men then, Marie Curie, some exceptional people, more or less agog over results. You know, and here's some new, this is just fake news. The stars were exactly where Einstein said they were supposed to be. That was the whole point of the triumph. And since then, we have had many additional tests of general relativity. The most dramatic in recent years was the detection of gravitational waves, both for merging black holes, merging neutron stars, that have told us that this beautiful, elegant theory that Einstein developed 100 years ago continues to triumph in every one of his experimental tests. And it's this theory that begins with these very elegant senses of symmetry and then describes, the properties of the universe on large scales. And it's two key concepts, and sort of it's two key equations, if you like, tell you, given how we know matter is distributed, this is how space will curve. Given how space is curved, this is how light moves. Right? And we just take those two pieces, we apply this on the scale of the universe, and then we discover, and when Einstein figured this out, he was disturbed. He didn't like this result initially, that this implies that the universe is expanding. And I think this is the conceptually most difficult idea we'll encounter today, because when we all have a kind of Newtonian or Galilean notion of space and time, and we think of things expanding, and you ask, well, what is it expanding into? And the name the Big Bang, I think, confuses people more, because it gives everyone a picture of an explosion that propagates out. That's the wrong picture. The picture to have is that the universe is expanding into the future. And the picture I think of is this is the universe today with a bunch of galaxies. We're on the surface of a beach ball. I think it's hard for most of us to visualize four-dimensional space, which is time. So we're going to visualize two-dimensional space plus one-dimensional time. We live on the surface of the sphere. The radius of the sphere is time. So as we go back in time, the sphere gets smaller and smaller and smaller. We go forward in time, the sphere gets bigger and bigger. The distance between objects grow. And I think when you see this, you realize as you go back in time towards what we call the initial singularity, the whole sphere collapses to a point. There's no special place in the sphere. The Big Bang didn't happen here or here or here. Every galaxy collapses down to this point. And this initial singularity, as we call it, is a moment in time, not a position in space. And this is when the expansion began. And one of the things we've learned through the observations that we'll talk about is this took place 13.8 billion years ago. and the universe has been expanding since. And I will cut off, though I'm happy to go into this in more detail, the initial question that most of you probably have at this point who haven't thought about the story in detail before. What's before here? I don't know. No one knows. Broadly speaking, there are two sets of ideas. This represents the beginning of time. There was no before here. Asking what was before this moment is like asking what's north of the North Pole. That's the answer that Stephen Hawking would have given. Another set of ideas is that there was something before here. It could have been a time reverse version of this, the universe collapsing in a big crunch. It could have been a quantum foam. But we don't know, and this is an active area of exploration. For me, my own work on this really began, or a central part of it was working with my colleagues on what we called the Wilkinson microwave anisotropy probe. And this is a project where not only is it named after David Wilkinson, who some of you may have taken physics classes with when he was a faculty member at Princeton, who died of cancer right after the launch, and was a key figure in its development. But so many of the people involved in this project were either faculty at Princeton, undergraduates at Princeton, or graduate students at Princeton. Probably 2/3 of the people involved on this list had a Princeton role. And this whole story is one that, going back to the observations, the first confirmed of the microwave background that took place on the roof of GEO in the 1960s, and Jim Peebles and Bob Dickey's theoretical work that helped earn Jim Peebles the Nobel Prize a couple years ago, back in 2019, Princeton has played a central role in the developments of the ideas that we'll talk about today. So what do we do with this satellite? We sent it out 4 times the distance of the moon. We went out, we mapped the sky. These pictures show the microwave sky at different frequencies. This is at our lowest frequency. The red stuff is the galaxy. That's the Milky Way. That's the smudge in the window. I like to think of it as we're looking out at a beautiful scene and there's some dead bugs on the window. And those dead bugs are the Milky Way. I have friends who study the dead bugs. That's interesting in and of itself. And we go to higher frequencies. The galaxy gets dimmer and dimmer. And what we want to do is zoom in on these regions and study them. And our goal is to remove the effects of the galaxy. And it's important to not ignore the galaxy. There's a whole other story I could tell that actually Joel knows parts of one of my former senior thesis students, who both did not hand his senior thesis in on time and published a major wrong result because he ignored the galaxy. And, since I knew early to check his work. So this is the universe's baby picture. This is the microwave sky around us. And this pattern is what we use to learn about the geometry and topology of the universe. This is a pattern of hot and cold spots. The variation in temperatures you see here are about a few parts in a few hundreds of thousandths of a degree variation from here to here. So these were very sensitive measurements. And the things that you should take away from this picture is it looks pretty random. In fact, statistically, it's very random. That tells us a lot about its physical origin. There's a characteristic size here of hot and cold spots, and we'll go measure that quantitatively. but that's actually the key thing we'll use to measure the geometry of the universe, is how big the average hot or cold spot is. And this picture, oops, there's Stephen Hawking's initials, represents a picture that we continue to improve. This is the data that was taken in 92. Here's the one I just showed. Here's the data in 2013. And I'll show you later on some data we have from 2020. We have better data in 2022, but we haven't released the paper yet, and the collaboration doesn't let me share this. And one of the problems about talking at Princeton is there actually can be people in the audience who could look at our data. Right? We have a pretty informed audience, so I won't show you the very recent things, but pretty new things as we go along. Actually, here's some higher resolution data that we got from Chile. So what do we want to do? Well, the first thing we want to do is measure the geometry of the universe. What do we mean by geometry? Geometry is a local thing that tells us about the curvature of space. If you live in flat space, and this is what Mrs. O'Brien taught me in 7th grade, the sum of the angles of a triangle is 180 degrees. And that's what a flat two-dimensional surface looks like. And we'll talk about in 3 dimensions, we can also define what flatness means. In 2 dimensions, you're on the surface of a sphere. Now, a sphere obviously is a 3-dimensional, a ball is 3-dimensional, but the surface of a sphere is just 2-dimensional. On the surface of a sphere, the sum of the angles in a triangle is greater than 180 degrees. And this is why if you fly to Paris after the reunions, you will fly up north towards the North Pole. That's a shorter distance than a straight line distance. And if the curvature of the universe was negative, the sum of the angles is less than 180 degrees. And geometry is very interesting because geometry in general relativity is destiny in most ways. If the universe is positively curved, the universe's expansion will eventually stop, and it will collapse on itself, and the universe's future would be a big crunch, a hot death. If the density is low, it keeps geometry as flat or negatively curved. It expands forever, gets colder and colder. Harlow Shapley, Princeton Star, I think 1918, who was a Harvard faculty member, described this at the Harvard Faculty Club to Robert Frost, who wrote the poem, "Some Say the World Will End in Fire, Others Say in Ice." And these are the 2 fates. These are also tied to the energy of the universe. This is 0 total energy. This is positive energy, negative energy. We could also think about the universe's geometry in terms of circles. And that's actually, I think, easier to generalize to more dimensions. In flat space, circumference equals 2 pi r. As you draw bigger and bigger circles, they get bigger. If you draw circles, let's see. Well, actually, now we'll go to from 2D to 3D. In 3D in flat space, the area of a sphere is 4 pi r squared. As it gets bigger and bigger, the area grows as r squared. We can measure that we're in flat 3-dimensional space by noticing that the flux from a star falls off as 1 over r squared. The flux that the Earth, as it moves its orbit a little bit further from the sun, gets a little cooler. We can observe that directly. Now let's look at the behavior of circles on a sphere. Well, if I start drawing circles around the North Pole, the circumference of the circle, as this radius grows, gets bigger and bigger until it reaches a maximum at the equator, and then it starts getting smaller again, and smaller and smaller. And actually, the circumference of a circle goes as a sine, which, if you remember, starts out growing kind of linearly, reaches a peak, and comes back down. And if we look at not circles in a two-dimensional space, but spheres in a three-dimensional space, it behaves like sine squared. And those of you who remember functions from 12th grade math, which are the ones we've probably all forgotten, in negatively curved space, it's a cinch. That's probably a word you have not heard since the math SATs. So the geometry is linked to the destiny. And we just measure the geometry because the characteristic size of all those hot and cold spots is set by what we call the sonic horizon. What's the sonic horizon? I'll send out a sound wave. It propagates out. The distance a sound wave moves in the age of the universe that we look at, we know how far that ought to be. Nature holds up a ruler to us. If the geometry is flat, the size of those hot and cold spots should be about 1 degree. If it's negatively curved, it would be about 0.2 degrees. If it was, if it was a spherical-like geometry, it would be more like 2 degrees. So we go back to our data, we measure it, and look at all the hot and cold spots. One way of doing that analysis is you can take the image you just saw, go to every single hot spot, and stack around it. And this is the pattern that we see around, actually I guess this one's around every hot spot. We find a cold ring of about 1 degree. We can actually observe most of the basic properties of the universe just from one of these pictures. That hot spot comes from a region that has, let's just do a cold spot. Cold spot here, a cold spot comes from a region that has an excess of dark matter. That dark matter sits there, forms a gravitational potential well that the photons have to climb up out of. By measuring the depth of that dark matter potential well, we can know how much dark matter there is in the universe. This ring, this hot ring, comes from electrons and protons and photons forming a fluid that moves out as a sound wave. We can measure how many atoms there are in the universe, its density, by measuring the brightness of the ring. We've got this ruler, this distance here, and that tells us the geometry of the universe. And from that, we can infer its age. We also learn a lot about the properties of the dark matter, and we can find out whatever we know. We don't know what it is, but we know what it's not. It's not ordinary stuff, because if it was ordinary stuff, it would be part of that ring. So we do quantitative analyses on this. We've plotted up in a function here, but this is just a way of representing the amplitude of these fluctuations versus scale. And the red line is our best fit model, and the points are the data we had at the time. And that gave us a measurement of the age of the universe, its composition in atoms, dark matter, dark energy, and what we learned about the properties of the universe. To me, the really remarkable thing is we took all this data, found that the universe looked flat, the simplest possible thing. The geometry you learned in junior high school is valid on the scale of the universe. The universe's total energy is 0. The universe's basic properties are described by 5 numbers: the age of the universe, the density of atoms, the density of matter, how lumpy it is, and how that lumpiness varies with scale. Those 5 numbers basically let me fit this curve. And that remarkable simplicity is just really, to me, shocking. That was the fact that the universe has been so simple when we went to observe it has been the greatest, I'd say, surprise of my professional career, its simplicity. And we've worked, this is almost a 20-year-old picture now, and what we've done for the last 20 years is try to break this model. We've made better and better observations. What we've done here in Princeton is we've done a lot of work going to Chile, to the Atacama. This is at a height of about 17,000 feet near the border with Peru, near San Pedro de Atacama. We built these radio telescopes. The world being a small place, my wife and youngest son Josh are here. We ran into Adrian Lee at the Dinky station earlier, walking over. Adrian built these. He's at Berkeley, and now we're getting together, building actually a much larger set of telescopes for the next generation of experiments, pushing even further. But what our efforts over the last 20 years have done is we've just kept pushing out in scale, measuring not just the amplitude of temperature, but polarization fluctuations of different kinds. The points here represent 5 different experiments, 2 from space, the one I was involved with here, the European-led Planck experiment, 3 different sets of ground-based experiments, the red points from Chile, the SPT pole, and the BICEP points from the South Pole. And the first thing to take away is a remarkable triumph of experiment. We have 5 independent experiments, 2 in space, different sets of detectors, some on the ground. They all see the same thing. We can do sort of point-by-point experiments, comparison in the sky, they get the same picture. And then this remarkable success of theory, when we look at the curve here, because that best fit curve came from the data that was 20 years earlier and only represents points, I have a pointer, up to that 3rd bump. Right? We took the measurements up to there with much bigger error bars. Data's gotten much, much better, much more precise. Basic model still fits remarkably well. And that to give a sense of what that pushes us to do. Well, right now we're working on building detectors that get at this point here and more measurements here and smaller error bars there, right? Because you keep pushing and pushing on something to see if it breaks, particularly if you have a theory like the one we've been driven to that has a universe filled with things like dark matter and dark energy, right? There's just a lot of stuff we don't understand. I mean, this is a story both of triumph in that we have a model that fits the data, but it's a triumph that leaves us with deep mysteries. We only know what make up 5% of the universe. So now, in the final part of the talk, I want to turn from the geometry of the universe, measuring its shape, to topology, and try to ask the question, is the universe finite or infinite? If I keep going in this direction, do I come back to where I started, or do I keep going forever? And one of the interesting properties of general relativity is it allows for both, both possibilities are consistent with it. And when I think about topology, I think about a donut. And one way of describing a donut is you can take a piece of paper, glue one side to another, this side to this side, make a cylinder, and then glue it together here. And if you're moving along the surface of a donut, you keep coming back to where you started. And you go this way, you come back to where you started. And that's mathematically equivalent to this picture, which might remind you of some video games we played earlier, like Space Invaders, where the aliens would leave on one side and come back on the other. That's a finite topology, that direction. And a lot of games have finite topologies where you stay in a square or, you know. When we started playing video games, they were all squares. We didn't have the technology for 3D. We'll look at 3D stuff with cubes later. But that's just, you know, the same picture. My colleague Neil Cornish, who did a lot of this work, is here too, also at reunions. He was a young postdoc then. And he was here working with us on this. He went to Cambridge, and I think this led to what I view as my greatest intellectual accomplishment. He explained this. They were filming Stephen Hawking, who he was working with, for The Simpsons. He explained to the staff of The Simpsons this basic idea. They immediately jumped at the donut theory of the universe. And there is a Simpsons episode in which I view myself as effectively being played by Homer Simpson, who explains to the Hawking character the donut theory of the universe. So, you know it's a good idea if Homer's advocating it. And there's lots of ways of gluing things together. You can take a shape like this, and if space is negative curved, you glue it together into a more pretzel-like shape. And there's actually a really rich and fascinating field of mathematics looking at all the different ways you can glue things together in 2 and 3D. I was at a party here in Princeton once when I was talking, you know, saying, I met someone at a party who was sitting off in the corner, who was a mathematician, and I tried to make conversation. And he said, "So what do you do?" I said, "Works in topology." I was all excited, and I said, you know, it was like no one's talking to us. Like, I said, "I've been thinking a lot about 3-dimensional topology." And he looked at me and said, "I only think about 2D. And that was it. That was like, he was, you know, if you were going to have a conversation with this guy. As an aside, to transition to what would have been my talk, I now work at a foundation that does a lot of work on autism and improving lives of people with autism. So here's our 3D version, and you know, again, just think of your 3D video game, where space is like that 3D video game. You leave through any wall, you come back. And there's lots of different ways of tiling space and time. Actually, an infinite number of ways with all kinds of interesting shapes. There's ways of tiling spheres. The one that you're most familiar with is, think about an orange, where you have orange sections. And imagine each orange section was identical. That is a tiling of the orange, where instead of having a space that is the size of the orange, you have a space that is the size of an orange slice. And you'd live in one orange slice and just keep going around. So that's, you know, it's a really fun area of mathematics. And you can tile things with spheres. And then we start to think about, what does this mean for the microwave background? And what would it be like to live in a finite universe? And if we lived in a finite universe, you would look out and we would see, because this is a copy of where we live. This is us. And remember, we're representing things like drawing those squares, where we can represent the universe with a series of identical cubes, right? We're in this universe. We're in this video game universe, where it's a finite cube. So when we look out that way and look at things there, that wall, we're looking at the same point. That's the same point as that, because those are glued together. So that means we see the same pattern in the microwave sky there as we do there. And whenever two spheres intersect, you get a circle. So what we want to look for are patterns of circles across the sky. And if we lived in this, what we call 3 torus, this cube with the walls glued together, we would see all these matched patterns of circles across the sky. And we go and we went to look for this. And could we see it? Well, that was the simulations of what we should see in a finite universe. We would see matched patterns at certain scales. And if the universe was infinite, we'd see none. We don't see any, didn't see any. And the data is improved, and we still don't see any. And there was a amusing experience that Neil knows, where for 24 hours I thought we saw it, because I took we're writing computer simulations, and I wrote these computer simulations that generated a file with some brilliant name like map.dat. And I overwrote my copy of the data and then ran a double-blind test on myself where I ran the simulations through the pipeline to look for this, assuming it was the real data. And if you run this, and the pipeline worked, and it found what was put into the simulations, which I thought was the real data for 24 hours. I emailed some colleagues. One colleague has, at Case Western has never recovered. And, but, you know, we all make errors in our research. If we're lucky, we catch them ourselves, right? And you go, you know, before you have a major announcement of them. And universe looks, we didn't see it, which means basically our universe is big. Universe is big, our universe is flat. Its universe seems to be incredibly, in some ways, simple. It's like the simplest choices were made on what led to its initial conditions and growth. Simplest, but of course also strange, because we have this dark matter that makes up most of the mass of our galaxy. We have dark energy that we don't know what it is. But it's filled with surprises. And I hope you have come away with this with the sense that it's been an amazing time in cosmology, that there are these kind of big theoretical questions about the shape of the universe, its fate, its composition, that we've been able to address with observations. And we're in a very, I would say, exciting state where we have learned a lot, but one of the biggest things we've learned is how little we know and how much more there is to discover. And I hope I've given you a sense of that, and thank you for listening. Joel.
So how do you reconcile the idea that it could be infinite with the Big Bang, which looks like a finite universe?
I think it's easier to visualize a finite universe that's very big, that's just bigger than we see, which is completely possible. That it's like finite, but not 13 billion light years across, but 1 trillion. But it is mathematically possible to start with an infinite universe and have it expand. So an example of I guess for me the easiest way to think about this is in one dimension, because it's just a line. And if you take a bunch of points on the real line, if you remember that. And imagine that today, every galaxy is at position 0, 1 million, 2 million, 3 million. And then when the universe was a millionth its present size, every galaxy then goes to position 0, 1, 2, 3, 4, 5. That's still, at time when the universe was a millionth its size, that's still an infinite line, but it shrunk by factor million. And that's sort of the weird, well, one of the weird things about infinity. It's really big. So you can keep shrinking it, and it still is infinite. Yeah?
Do we have an understanding of whether the geometry was always flat, or was it flattened by inflation, or flattened by dark energy?
Somewhat. So let me explain the evolution of the geometry. If the universe was truly flat, it stays flat for all times. But if it was slightly positive, so that its expansion would stop and turn around, the curvature that I would measure, gravity wins. And if it was like, if 0 is, actually, you stand away. 1 is flat, and the geometry, and the actual number was 1.00001. When the universe was 1,000th its current size. Today it would be 1.1, and soon it would be 2 and 3. It runs away.
Okay.
So, in the standard expansion, flat is like an unstable point. It's like balancing a pencil on a point. You just let it go, it quickly falls one way or another. So the fact that the geometry is so close to flat was initially a surprise that we would end up, and I actually remember, and I wish I had notes from this. I threw out my notes from my sophomore year quantum mechanics class with Jim Peebles, where Jim got up and he said, I have finished the material that I wanted to cover. I'm giving this bonus lecture. And he explained all this stuff about the geometry of the universe, explained the work he was doing in 1980 that got him awarded the Nobel Prize in 2019. And he gave it to the class. And I've emailed, Dan Arovis was in that lecture, Greg Moore was in that lecture, I think Karen Rabe was there. None of us have the notes. And, I had the pleasure of going to the ceremony in Stockholm, and was just, I really wanted to be able to bring those notes to there. This strangeness was one of the things that led to the development of a theory called inflation. And the idea in the inflationary model is in the very early stages of the universe was dominated by something that looks a lot like dark energy that drove an incredibly rapid expansion. And the idea with inflation is that it has this exponential expansion, and it expands so rapidly that it stretches it. And the picture to think about is you've got some ball that you stretch enormously, and when you stretch something enormously, it starts to look flat. And I think that is the best explanation we have at the moment of why it's so close to flat, that the universe experienced this incredibly rapid period of expansion early on. That's reinforced by the fact that if you look at the predictions of that theory, which was developed in the mid-'80s, it predicted the pattern of fluctuation should be the random pattern that looks just like what we saw 20 years later. So all our observations are consistent with the inflationary answer to this question. But we still would like to do a few more, we don't have kind of the silver bullet evidence for inflation. What that would be the detection of gravitational waves from the early universe. We have seen gravitational waves. It's been one of the great things in astrophysics in the past few years, but they have been from nearby objects. Black holes colliding, neutron stars colliding, fascinating systems, but not from the early universe. And one of the things we're doing right now in Chile, people are doing in the South Pole, is looking for the gravitational waves to be the test of inflation. Yeah.
We didn't have so much dark matter or dark energy back in the day. Can you talk a little bit about what it is? Is it just a plug? Is it good for anything? Is it knowable?
It was there, we just didn't know about it. The first evidence for dark matter actually goes back to work by Zwicky in the 30s, and was subsequent work by Vera Rubin and Albert Bosma in the 70s and 80s. So dark matter makes up most of the mass of our galaxy. We don't know what it is. It behaves like ordinary matter in terms of its gravitational effects. So the simplest set of ideas we have is there's some new particle that we haven't detected yet. It took us a long time to detect neutrinos. There's lots of stuff that interact weakly that's hard to see. So dark matter probably represents some new kind of particle, some physics beyond the physics we have learned so far. It is the biggest hint we have that future experiments, like the Large Hadron Collider, might discover something new, because we know from cosmology there's new physics to discover with dark matter, and we can constrain some of its properties from these observations. The evidence for dark energy was not there when we were undergraduates, and it has been built up over the last 40 years. The earliest, well, there's actually the tipping point, like most ideas, its history is much richer than the story we tell. The tipping point evidence was the measurements of supernova that led to the Nobel Prize to Adam Rees and Brian Schmidt and Saul Perlmutter. We don't know what dark energy is. It seems to be energy associated with empty space. So the simplest idea is something we call vacuum energy, that space itself is energy. We know in quantum mechanics that there should be what we call vacuum fluctuations. Those vacuum fluctuations are pretty important. Like if there weren't vacuum fluctuations, things like transistors and stuff wouldn't work. So we sort of take advantage of them on scales. And when we try to connect vacuum fluctuations to the scale of the universe, we don't really know how to make the connection. Some of that is because 20th century physics has two great ideas: general relativity and quantum mechanics. And what is the great quest of 21st century physics for fundamental physics is tying the two together. And there's been a lot of work in things like string theory, and that's just all attempts to tie them together. And despite 30 years of effort of some of the smartest people I know, we've not been able to really fully develop a successful thing that we call string theory that explains everything we see. So we don't know what quantum mechanics really predicts about the properties of the vacuum. And one way of understanding the dark energy is to say, it just happens to have this value. It's a value that's really small. We don't know where it comes from. But this also motivates a lot of what we're trying to do in cosmology now, is get a better handle on these questions. Well,
I have a professional question for you. How are you balancing your scientific research with your new role
as Foundation president? Well, first, I've given up long ago watching sports on TV. I'm trying to spend my Fridays doing research and staying connected to projects. So I try to keep Fridays clear. I continue to have emeritus status here. I guess emeritus status you kind of get forever till you die. Maybe it continues after death. I don't know. I haven't checked. And I have working with me right now some really wonderful graduate students. And for a while I've been saying, like, people ask, what like language do I program in? What computer language? Graduate student, right? And I go and I like sketch out what to do, and these smart students do the work. So that's continuing to have conversations pretty regularly with some excellent students and postdocs have let me keep my hand in. And in fact, I'm going to be staying till Monday. In addition to bringing this outfit, I brought my academic gown because I'm graduating one of my thesis students. I'll be hooding her on Monday, which will be fun. Let me just take one more question in the back.
David, at the beginning of your talk, you mentioned the miraculous congruence of mathematics and physics. Francis Collins and others have looked at that and some of the cosmological discoveries, research you talked about, and as evidence of the existence of God. And from your perspective and from what you have seen in your research and what you are working on, how do you approach those arguments?
Yeah, I think you have to approach all those questions, and even questions of origins themselves, which tie in with this, with a lot of humility, right? I think we heard a nice talk on this recently by Frank Wilczek, where he talked about science tells us about what is, and that informs what could be. And, I think the existence of God is really about what could be. It could be the answer to some of the things, the deep things we don't know. But I think what's even more important in that system of what is and what could be is what should be. And science helps us in that because it gives us what is informs what could be, and that's what forms what should be. But that is ultimately, I think, the role of religion and ethics, is science doesn't guide us to what should be. And that's where, when I think about that system, that's where I see religion and ethics playing a role. Good, thanks.